Welcome everyone to the Sheffield Machine Learning Lecture Series brought to you by the Machine Learning Group from the University of Sheffield. I'm Aditya Gilra, a lecturer, that is assistant professor there. We are very pleased to welcome Professor Moritz Grosse-Wentrup from the University of Vienna. So brief introduction. He did his PhD in electrical engineering and information technology from the Technical University of Munich, 2008. He was then a postdoc at the Max Planck Institute for Biological Cybernetics, this was in Tübingen, 2008 to 2013. And then he was a group leader at the Max Planck Institute for Intelligent Systems in Tübingen as well, 2013 to 2017. And then professor for data science at the University of Munich, 2017-2019. And then from 2019 onwards, he has been a university professor of neuroinformatics at the University of Vienna. So we are very glad to welcome again Professor Moritz Grosse-Wentrup. He will be talking to us about multi-level causal modeling, and we look very much forward to his talk. Welcome again, Moritz. Stage is yours.
Thank you, Aditya. Thank you for the kind introduction, and thank you very much for the invitation to speak here. So I'm going to switch now to and Aditya, if you could briefly let me know if everything indeed looks the way I intended to work. So can you see the slides well?
Yes, looks good.
Excellent, good. So hello, everyone, and thank you for attending. So I want to talk about multi-level causal modeling today. And my talk is going to have 3 parts. And the first part, I want to motivate multi-level causal modeling from a cognitive neuroscience perspective. So I'm very much interested in bridging the explanatory gap between neuronal activity and behavior and cognition in cognitive neuroscience. And I personally believe that multi-level causal modeling provides the opportunity to be a rigorous mathematical framework for doing so. So the first part will be this motivation in cognitive neuroscience. Then I'm going to switch to the causal side in the second part and explain what exactly I mean by causally consistent modeling across multiple levels. And then in the third and final part of the talk, I'm going to present some ongoing work on how to actually learn causal models across multiple scales. So I would like to begin with a rather fundamental question and talk about what actually specifies the conceptual framework. And I want to do that with an example from a rather old book by the German mathematician David Hilbert. I read his book, Grundlagen der Geometrie, Foundations of Geometry, a long time ago, and it was really an eye-opener to me. And what he writes in this book is the following. He says, let us consider 3 distinct systems of things. The things composing the first system we will call points. Those of the second we will call straight lines, and those of the third system we will call planes. And something that really struck me here is that he doesn't say there are points, lines, and planes, but he says there are just 3 types of things. And we call them points, lines, and planes, but we could call them anything else. It doesn't matter. Because the names, that's not what gives meaning to these objects. What gives meaning to the objects is the following. The axioms of geometry establish a connection between the concepts indicated above. So let me give you one example. His first axiom says that 2 distinct points, A and B, always completely determine a straight line A. You write A equals A or BA equals A. Now, so 2 points are a line. And here's another axiom, 3 points ABC, not situated in the same straight line, always completely determine a plane, alpha. We write ABC equals alpha. And what I find so fascinating here is that these different systems, these different things, these concepts in such a framework, they don't have any meaning on their own. They only acquire their meaning through the relations between them. And once we have that in mind, I think it's natural to ask, when we talk about cognitive neuroscience, well, what are the concepts that we talk about in cognitive neuroscience? And what are the relations between concepts in cognitive neuroscience? And well, we can model a person at various levels of granularity. For instance, we can model this person on the cognitive level and use cognitive concepts and relations between them. or we can model the same person on the neuronal level and use a concept such as firing rates of neurons. Or we might also go to even smaller scales and model a person on the biochemical level, or maybe even down to the quantum theoretical level at some point in the future. Now, on each of these levels, we're used to working with certain concepts. Yeah, from the cognitive level, we may have concepts like openness and neuroticism and happiness. And on the neuronal level, we may have concepts such as neurons 1 to 4 and their activities, their spikes, their probabilities to spike, or their mean firing rates, or whatever we choose to represent these neurons. And now I think we should ask ourselves the question, what sort of relations hold between the concepts on each of these levels? And if you think about how we talk about such concepts, for instance, on the cognitive level, then we say things like, well, openness, the openness to new experiences makes you more happy. Or neuroticism, if you're a very neurotic person, that makes it a bit more difficult for you to be happy. And in this language, yeah, openness makes you happy, that's causal terminology. Yeah, so we think that openness might be a cause of happiness. And I'm going to denote that by these directed arrows here. And on the neuronal level, I think that is pretty similar. We say, well, neuron 1 firing might cause neuron 2 to fire, and so on. So I would claim that in cognitive neuroscience, at least, relations within each of these levels are of a causal nature. And that has some interesting implications. So that means that these different concepts like openness and neuroticism, they must be separate. We must be able to intervene on these concepts separately. For instance, intervene on openness with, I don't know, maybe some sort of psychotherapy, while leaving neuroticism alone. And on the neuronal level, we must be able to intervene on one neuron, maybe by sticking an electrode into it and making it fire, but leaving other neurons alone, because these are separate causal concepts. And I would hope that these causal relations are used to model relations within one conceptual framework is reasonably uncontroversial. But now, what about the relation between these different levels? If we want to link them, what sort of relations could hold between the neuronal and the cognitive level? And first you might ask, well, why not causal as well? Why would not it be possible to say some neuronal activity pattern causes openness or causes happiness? And of course, you could say that, but I don't really think that makes too much sense, because it would imply that happiness and neuronal activity patterns are separate things, that you can intervene on one or intervene on both of them individually and separately. And I don't actually think that's what we want in cognitive neuroscience. I think we want a different type of relation. And I want to illustrate the type of relation with a quote from David Papineau, whose paper, Mind the Gap, I found very influential. And in that paper, he writes the following sentence. He says, I think physicalism is best conceived as a thesis of identity between conscious properties and material properties. And identities need no explaining. The boldface is by me. And I think there are two very, very important ideas in here. If you accept physicalism, then there should be an identity between conscious cognitive states and neuronal states. It shouldn't be that neuronal states cause cognitive states, but they should be identical to cognitive states. One certain neuronal activity pattern should be identical to a certain cognitive state. And the second important point is identities need no explaining. And he illustrates that with one example, and that example is water equals H2O. So imagine that you are some alien chemist, and you have learned all about chemistry on your alien world, and you know about H2O. But when you look at what humans do, they always drink water or drink something that they call water, and you have really no idea what that should be or why they do that, until somebody points out to you that water is identical to H2O. And then it all makes sense to you. And once you know that H2O and water are the same thing, it doesn't make sense anymore to ask why. You can reasonably ask, why didn't I know that before? Or why did I believe they were not the same? But once you have established that there's an identity between water and H2O, you have reached the deepest level of understanding that there is. Asking why doesn't make any sense anymore once you have established this identity. And I think that if we believe in physicalism, or I would agree with David Papineau, that if we would be able to establish such an identity relation, or also called a constitutive relation, between the neuronal level and the cognitive level, then we would have learned everything that there is to know. Then we could explain that certain neuronal activity patterns are identical to certain cognitive states, and it wouldn't make sense anymore to ask why. We would have reached the deepest level of understanding. So this is how I think about this problem of relating neuronal to cognitive states. And you can reasonably ask, well, is that so novel? And in a way, no, it's not very novel. Yes, David Marr already in his book, Vision in 1982, wrote about these levels. And he said, the effort is to show that in principle, the microscopic and macroscopic descriptions are consistent with one another. One must be prepared to contemplate different kinds of explanation at different levels of description that are linked, at least in principle, into a cohesive whole. And there you already find these ideas, microscopic world, macroscopic world, and somehow they should be linked to one another. And David Marr brings these three important or very famous levels: the computational level, what is it that a system actually computes? The algorithmic level, what kind of algorithm does it implement? And the hardware level, how is this algorithm implemented physically? But he explicitly states in his book that these are just three examples. There could be many other levels. And the challenge is relating these levels to one another. And these ideas have recently been picked up again by Krakauer in his paper, Neuroscience Needs Behavior, that I really liked, where he writes, causal mechanistic explanations are qualitatively different from understanding how component modules perform the computations that then combine to produce behavior. Or in other words, he believes that causal mechanistic explanations are not enough. We need something more. And then he goes on, the conceptual point is that the ion channels do not cause the cardiac rhythm. Instead, the rhythm just is the combination of the higher level of the cell membrane and the lower level of ion channels. And there again, you find these identity relations. And he illustrates this nicely here in this drawing here, where he says we have three axes here, the behavioral level and then neurons. Then here have mass, three levels, 1, 2, 3, and causal manipulation, understanding. And he believes we are somewhere here currently, that we're mostly looking at neurons and at their hardware implementations and causal manipulations of that. But where we actually want to get to is an understanding here of behavior, so linking to a new level. So these ideas that I'm sketching here, they're not new, they've been around for a while. So what is novel here today in my presentation? I think what is novel here is that I'm going to present a rigorous mathematical framework to talk about such relations, and a framework that is generic enough that it can be applied in principle to any level. And I'm going to sketch some ideas and ongoing work how to actually learn causal models across these multiple scales. So that concludes the first part of the talk, and I'm going to move on to the second part. So I'm now going to talk first about causal consistency. What does it mean actually for two models to be consistent to one another, and in particular to be causally consistent to one another? And then I will talk about how to learn such transformations, first from a macro level to a micro level perspective, and then very briefly at the end, the other way around. So I want to begin by talking about the causal framework that I want to work in. Yeah, so I said within each level, I believe that causal frameworks are the right way to think about relations, and then we must pick some causal framework. And I believe that the framework of structural equation models, for instance, as described in Judea Pearl's seminal book, Causality, is the most rigorous and flexible framework that we currently have to talk about causal relations. So I briefly want to introduce these structural equation models. So a structural equation model is a triple that consists of x, f, and epsilon. And the x is a set of endogenous variables, the concepts, the states, the variables of your model. Epsilon is a set of exogenous noise variables, so things that drive your system but that you do not explicitly model. And f is a set of functions. And each of these functions determines the value of one of those concept variables as a function of the parents of that variables and a noise term. And the set of functions is constrained such that no xi is a cause of itself, such that you don't get any cycles. And the structure of such an equation model is frequently represented by a directed acyclic graph, for instance, like this one here. And the nice thing about this graph is that it makes it really easy to argue about distributions and effects of interventions on distributions. So these structural equation models give rise to a probability distribution over the variables in X due to the distributions of the noise variables and the functions. And this joint distribution factorizes according to this DAG. So the joint distribution over X, if you write it down with the Bayes rule, and then eliminate in the conditional part all those variables that are not causes of the respective variables, you end up with this factorization according to this DAG, where you have x4 at the end because that is the root cause of everything, next 2 at the beginning because this is the end effect of everything. And then you can represent interventions in this framework by the so-called do operator. Now, for instance, you write the intervention of setting x1, the variable x1 to the value x1, as the probability distribution of x given do x1 equals x1. And to write down that probability distribution, you go to this factorized distribution here. You replace every x1 in the conditional part by the specific value that you set it to, and the term that the probability of x1 is set to 1 because you set it to one specific value, and hence this term just becomes 1. And this is then your interventional distribution, and that is how you reason about the effect of interventions in structural equation models. Okay, now with this introduction, I now want to give you an example, a motivating example, what sort of relations we would like to hold between different structural equation models across different levels. And this example is inspired by cardiology. So in cardiology, we care about heart disease, HD. And it was believed for a long time that the total level of cholesterol, TC, has an influence on heart disease. But then people found out that it's a bit more complicated and that there are 2 types of variables, low density lipoproteins and high density lipoproteins. And actually both of them have an effect on heart disease. And what we considered as total cholesterol before is the sum of the 2. So we have a mapping here between a micromodel that has these 2 states, LDL and HDL. And if we add them up by some transformation tau, then we arrive at this macro model here of total cholesterol and heart disease. And now we can ask this micromodel and this macro model, do they stand in a consistent relationship to one another? And if not, why not? And I want to illustrate that with some simulated data inspired by this example. Yeah? So this is not real data, it's simulated, simplified data. Let us assume that HDL and LDL are binary. They can be high or low. And low means -1 and high means +1. And so we have a total of 4 different states of HDL and LDL. And for each of these states, we get a certain distribution of heart disease. And now if we take this data as the ground truth and map it via this tau here to this macro model, then we get this distribution here. Now we only have 3 different states, so we have reduced the number of total states. And for each of these states of total cholesterol, we have a certain distribution of heart disease. And now, a priori, there's nothing wrong with this transformation. It's a perfectly valid transformation. But I now want to argue that it's not a causally consistent transformation, and it's not what we want, for the following reason. Consider interventions on the micro level. There are 4 different types of interventions. You can set HDL and LDL to all of these 4 combinations. And now if you set HDL and LDL to -1 and -1, then you get this distribution here of heart disease. Now I would like to ask, is there a matching intervention on the macro level? So can I set TC to a certain value and get the same distribution over heart disease. And yes, I can either set TC to -2 or to +2 and get the same distribution. However, this is already not very nice because there are two different states on the macro level, two different types of interventions that give me the same effect. Okay, but gets worse. Say we do another intervention and set HDL and LDL to +1 and to -1. Then we get this distribution here of heart disease. But on this macro level model, there is no state of TC that gives you this distribution. So there's no mapping from this intervention on the micro level to an intervention on the macro level that would have the same effect. And hence, I would argue that these two models here, they are observationally consistent, but they are not causally consistent, because you cannot match interventions on one level to interventions on the other level while having the same effect on the outcome variable. If, however, you define a new intervention, tau prime, that gives rise to TC prime, where you subtract HDL and LDL from one another, then you get this distribution. You again get three states, but now this is a causally consistent transformation in the following sense. For any intervention that I do on the micro level, I can find a matching intervention on the macro level that gives me the same distribution over heart disease. For instance, this intervention, -1 and -1, maps to TC prime being 0. 1 and 1 also maps to TC prime being 0. This micro intervention maps to this macro intervention. And this micro intervention maps to that macro intervention. And now I can reason about the effect of interventions on heart disease on both levels. And I have not lost any causally relevant information. And I would like to argue that this is the type of causal consistency between micro and macro models that we would like to have. So to make this a little bit more rigorous. And this is a work that we published at ULI in 2017, and the work has been mostly done by these two guys here, by Sebastian Weichwald and Paul Rubenstein at the Max Planck Institute for Intelligent Systems. So here's the crucial definition that is at the heart of this paper. Let's say we have two structural equation models, mx and my. And you can think of these mx as the micro level and my as the macro level. Maybe mx is neuronal and my is cognitive. And on each of these two levels, we have a set of interventions. So we do not allow all interventions, but we specify which type of interventions or interventions on which variables and to which values we allow on each model. And we have a mapping tau between the concepts, the variables of these two models. So this is kind of the observational mapping. Then we say that my, the macro model, is an exact tau transformation of the micro model mx if there exists a surjective and order-preserving map omega that maps the interventions to one another. So for every interventions on the x level, the omega maps that intervention to an intervention on the y level. And this intervention map should be surjective, so that you can map many micro-level interventions to one macro-level intervention, and order-preserving, such that if you combine and compose multiple interventions on the micro level, you should also be able to do these compositions on the macro level of the matching interventions. And then we require that this observational property here holds. And that means that if you look at the probability distribution, after doing an intervention I on the micro level, and then switch to the macro level via this tau transformation, that the probability distribution that you get is the same when you start on the macro level, on the y level, and do the intervention that is the matching intervention to the one on the micro level on the macro level. And we want this to hold for all interventions on the micro level. And then you can prove that if this actually holds, if there exists such a transformation, then the following diagram commutes. And this diagram expresses the following idea. You have here in the top row, the micro level, the unintervened distribution, the distribution after the intervention I, and the distribution after adding the intervention J to the intervention I. And here you have on this, in the second row, the macro level representation. And via the tau, you switch from the micro to the macro level. And the omegas here, this is the switch from the micro level interventions to the macro level interventions. And that the diagram commutes means that you can go from here to here via any path. You can first do 2 interventions on the micro level and then switch to the macro level. Or you can switch to the macro level and do the matching interventions on the macro level. Or you do the first intervention on the micro level, switch to the macro level, and then do the second intervention, and you always end up in the same state, such that you can interchangeably argue about the effects of interventions on the system on both levels. And I would argue that this is exactly the type of consistency, of causal consistency, that we would like to hold between different levels, between different structural equation models that model the same system at different levels. So going back to our initial example, these constitutive relations between levels, I believe, should be given by these transformations tau and omega. So constitutive relations between levels, causal relations expressed by structural equation models within each level. And now that we have such a framework, and I would like to emphasize have an empirically testable model, or we could come up with empirically testable models. The question is, of course, how do we actually learn these? And one way that you could approach this is that you say, well, I first use all those tools for causal inference that have been developed over the last, say, 2 decades to first come up with a neuronal model, and then with a cognitive model. And then I try to learn transformations tau and omega to map these two to one another. I personally believe, though, that that is unlikely to succeed, because these concepts that we are used to on the cognitive level and maybe also on the neuronal level, they have been set or derived without having these transformations between levels in mind. And in cognitive science, we have concepts that have been around for a long time before we were able to record neuronal activities. And who's to say that these concepts are the right ones to find consistent transformations between the neuronal and the cognitive level? Maybe we need to refine these concepts and come up with new concepts that better represent what is actually going on in our brains. So our approach is to do this differently and say we either start at the macro level and try to move to the micro level, or we start at the micro level and try to move up to the macro level. And interestingly, I think by now that these two ways are more related than I had previously thought. So now I want to first talk about how to move from the macro to the micro model, and then very briefly in the end, discuss a little bit how to move from the micro to the macro model. But I should emphasize that all of this is really ongoing work in progress. Yeah, so we don't have too much to present there already. So I would like to start with this macro model thing. And this is work together with and mostly done by Alex Markham at the University of Vienna. And that work is going to be published at UAI this year, and you can already find a preprint on arXiv. So we started thinking about this work about what is the most macroscopic level at which you could model a system. And the problem here is that even if you start with rather macroscopic variables like happiness and openness and so on, you already posit that some cognitive states in a way exist. And we didn't want to do that. We said, well, why not take the most macroscopic level as the one that is objectively there? And to us, that is data, measurements. Say you have 4 measurements, and maybe you can think of these measurements as 4 questions on a questionnaire, and every subject can fill out each of these 4 questions in 1 to M4 on a scale from, say, 0 to 10. And now these are not causal concepts, because it wouldn't make sense it wouldn't change anything how a subject feels if you take a pen and cross out one measurement and write down something else. This is just objective data. And now we can ask the question, well, how many concepts do you actually need to explain these measurements? And if you look into the psychology literature, then typically what people invoke are factor analysis models or maybe independent component analysis models. And essentially what is done in these models is that you posit as many latent variables as you have measurement variables. And typically assume that all latent variables a priori affect all measurement variables. And then you try to learn these functional relations from the latent variables L1 to L4 to the measurement variables M1 to M4. But in cognitive science or psychology, you typically try to construct these questionnaires in a way that they measure different things. If they would all be dependent with one another, then probably you wouldn't have designed a very good questionnaire. So empirically, what you would want is certain dependency patterns emerging in your measurements. And let us assume here in this example that these edges, undirected edges, denote pairwise dependencies, such that M1 and M2 are dependent, M2 and M3 are dependent, and M3 and M4 are dependent, and M1 and M3, but M4 is independent of M2 and M1. And now this latent model with these 4 latents that have an effect on all measurements, that actually would imply a dependence between all 4 variables, because every variable has a common cause. And that is obviously too much. You don't need that to explain these dependency patterns. So we asked ourselves the question, if we have such measurements with certain dependency patterns, what is the minimum number of latent variables that can explain this dependency pattern? And in this example, it's reasonably straightforward to work that out. This is a solution where you just have 2 latent variables. L1 is a cause of M1 to M3 and gives rise to these dependencies. And L4 causes M3 and M4 gives rise to this dependency here. Now, this is reasonably straightforward. But how do you do this in general? If in general you have an arbitrarily complex number of measurements and some complex dependency structure between these measurements, how do you find the minimal number of latents that can explain your dependency patterns? And the thing to note here is that, that was one of our main insights, that these 2 variables here, these are 2 separate maximal cliques. So a clique in a graph is a fully connected subset, and a maximal clique is a fully connected subset that you can't, to which you can't add another variable such that they remain fully connected. So here you have 2 maximal cliques. And it turns out that for each of these maximal cliques, you need to posit 1 latent that can explain the dependencies within this maximal clique. And that is the minimal number of latents that you need. So to make this a bit more precise, we defined these measurement models, which are essentially structural equation models, just that we split up the nodes X into latents and into measurement nodes, and they don't intersect. And all measurement nodes have at least 1 incoming latent or 1 incoming edge, but they don't have any edges that go out of them because they're just measurements. And the latents, they have an out degree of at least 1, so they cause at least 1 measurement variable. And then we define a minimal measurement causal model, or minimum MCM, for a set of measurement variables as the least expressive MCM that is observationally consistent with M. And this least expressive is not that easy to justify, and I don't want to go into too much detail here, so please look it up in the paper. Essentially, you say that if a model can induce all dependencies of another model plus additional ones, then it is more expressive than the other one. And then we figured out that the problem of finding such a minimal model for a set of measurement variables can be framed as a graph theoretical problem of finding a minimum edge clique covering over the corresponding undirected dependency graph, as I illustrated in the previous slide. And then the main theoretical result that links now to this causal consistency is the following. For a given set of unconditional pairwise dependencies among measurement variables M, a min MCM gives a lower bound on the number of latent variables required in any faithful and observationally consistent MCM. So in a sense, a min MCM is the most macroscopic model that you can come up with for a certain set of observations. So going back to our example here with this min MCM of 2 latent variables, there are certainly many more latent models that are consistent with these measurements. For instance, you can here add another latent and add this connection between L1 and L2, and that is also consistent with our observations. But it's not a minimal one because you have a larger number of latents in here. But of course, you might want to have that. You might want to refine your model further and further and add more and more latents to have a more fine-grained model. And maybe at some point you come to the level that you want to model it at. But these reasons always have to respect the properties of the min-MCM in the following sense. This min-MCM, in a way, compartmentalizes your model. And within each of these compartments, you can refine your model as much as you want, but the min-MCM posits that any observationally consistent model cannot have a causal link from one latent in one box to another latent in another box. So that means if we go back to our initial example, now we could start with measurements of happiness and maybe other variables, see how many cognitive concepts we need to explain our measurements, and then maybe we find that we need two, but per se they don't have any names. But we can now give them names. We can now look at which questionnaire questions, for instance, they influence, and how they overlap in the questions that they influence and how they do not overlap, and come up with matching names. And in this way, hopefully refine the concepts in cognitive science that we currently use in any causal fashion. And once we have this most macroscopic causal model, latent causal model, we can then start refining it. And hopefully at some point we will be able to refine it such that it becomes consistent with a neuronal level model. But I think this is still rather long off, and this is a part of ongoing work in our group. So I'm slowly getting to the end. And I want to conclude with briefly talking about transformations from the micro level to the macro level. And this is something that we really only realized how related that is to this min-MCMs after we had done it the other way around. So imagine you have an arbitrary DAG at some micro level, and you have these variables x1 to x7. And maybe these are neuronal activity patterns, firing rates, or whatever. And now in any DAG, because it's a directed acyclic graph, you have some nodes that are sinc nodes that don't have any outgoing edges. And you have some nodes that are source nodes in the sense that they only have outgoing edges. And that means that you can take any arbitrary DAG and split it into a measurement model. So for instance, here, the variables x5, x6, and x7, they don't have any outgoing edges. So you might call these three variables measurement variables, say M1 to M3. And then you can check which dependencies are induced between these measurement variables here. And if this is the true micro DAG, then the dependencies will simply be M1 and M2 will be dependent, and M2 and M3 will be dependent. And now you can invoke the MeDIL causal framework and come up with a macro model and say, will you model X1 and X2 as one latent and X3 and X4 as one latent. And now you know that this is the most macroscopic model that you can come up with if you keep these sinc nodes and nodes as your measurement nodes. Now, because you know that the other way around, any other model must be a refinement of our min-MCM, there must be a causally consistent transformation between these two levels. And how to learn and find these transformations is something that we're currently looking into in our group. So with that, I already would like to come to a conclusion. So I've argued that systems can be modeled at various levels of granularity, and that relations within each level are causal, and relations between levels are constitutive. And that if we want to really understand a system, that actually means that we want to find causally consistent mappings between these levels. And once we have found these levels, these mappings, I believe from a scientific point of view, there's nothing left to be explained. And I hope I have convinced you that the framework of causally consistent transformations between SVMs provides a rigorous and generic framework to think about such transformations, and importantly, to also be able to empirically test such explanations. However, of course, there remains a lot to be done, and there are many open questions. For instance, something that I find very interesting and certainly a topic for future work is exact causal consistency realistic? Will it really be possible to take a neuronal system and abstract it in such a sense to a cognitive level that you don't lose anything that is relevant. And probably I would think that that is not the case. Probably you have to give up something. So I think we also need some form of approximate causal consistency, such that we can move between levels, but have causal guarantees in the sense that on the macroscopic level, our causal predictions, the errors of our causal predictions will be bounded. And then, of course, going back to more the cognitive neuroscience, even philosophical perspective, is physicalism correct? Everything that I've argued here obviously only makes sense if physicalism is correct and if mental states are not more than physical states in the end. And I would think that most scientists agree with physicalism nowadays, but some do not. But to me, the important thing is, I think this framework that I've presented here, in principle, makes it possible to test that. And we should be able to find a causally consistent mapping between neuronal and cognitive levels via structured equation models and the mappings between them. Then I think that would be nice evidence in favor of physicalism. So that brings me to the end, and I only have one final slide, and that is a job ad. So I haven't talked about applications at all today, but we have an application. And as of today, June 4th, 2020, we have an open PhD position in a European project, the ZEbrafish Neuroscience Interdisciplinary Training Hub, where we work with groups all over Europe on zebrafish and calcium imaging in zebrafish. So this is a picture of neurons in the brain of a zebrafish on causal modeling, this project for us. So our task, or our goal in this EU project is to apply all those theories that I've outlined today to zebrafish imaging. And the cool thing about the zebrafish is that they have a reasonably complex repertoire of behaviors, but not too complex. They can swim, evade predators, and so on. And we can do whole brain or close to whole brain imaging, or our partners can do that in these brains, in these fish. And so I believe for this model system, we have a reasonable chance to apply these ideas of causally consistent modeling across different levels, and hopefully get some interesting results. So if you should be looking for a PhD position and you are interested in this topic, please get in touch with me, send me an email, or you can also take a look at the webpage of the ZENITH program. So thank you very much for your attention, and I'm looking forward to your questions.
Yeah, thanks a lot, Moritz. Wonderful talk, very clear. We have some questions, and some have been upvoted. So let's go for the upper ones. Maybe I will just invite the user on the screen so that you could maybe, I don't know, we need to share. But anyway, I'm inviting Mark Axon onto stage. Mark, could you come on and ask your question on screen?
Hello?
Hi, Mark.
Hi. I'm Mark Axon. I'm a master's student in statistics at Columbia University. So I guess my question is, so I'll just read it off. So one of the central challenges of causal inference in neuroscience is that we're observing a very small number of variables, right? So let's say we're observing time series of voxels, and we want to draw the true causal relations on different levels, like you said. But there are many possible confounders, and their distribution is completely unknown. Yeah. So how can we say that? And then let's say with the methods you described, we can obtain a causally consistent model. How can we say that it's at all related to what's underlying it?
Yeah,
the true causal relation.
Yeah, thank you for the question. So there are two answers. The one answer is the reason for the zebrafish modeling is that I believe we need to get as close as possible to the ground truth to minimize the risk of confounders to be able to do something like that. And if you would apply this framework to, say, fMRI data or EEG data, I very much doubt that any useful results would come out of it. Yeah, so I agree, confoundedness is a huge problem. I would hope, though, that in the future, when we have also a framework for approximate causal consistency, we can deal with some confounders. And certainly this would mean that our transformations wouldn't be exact anymore. We wouldn't make mistakes. But if we find a framework where we can bound these mistakes and say, provably, we won't be off by more than some epsilon, then I think that would be a step ahead. But I fully agree, confoundedness is one of the major problems.
Thank you.
Thanks.
Thanks for the wonderful talk.
Thank you very much.
Yeah, thanks, Mark. Let's invite Nada Abdul Rahim. She's from Sheffield, actually. I'll just invite her. Please come on to ask your question, Nada.
I read the question, and I think I can, if there are problems coming on, I can already start answering it.
Sure, I think, yeah.
Thank you for that question to clarify. So the question is, if M1 depends on M2, M2 on M3, M3 on M4, and so on, doesn't that mean that all the measurement variables are dependent with one another? And in general, no, that is not the case, because it depends on how the dependency comes up. Imagine, for instance, that say you look on the street outside, and you check whether people are wearing a coat. And what are the reasons for people wearing a coat? Well, maybe because it rains outside, that makes people wear a coat. Or maybe, I don't know, it's not a good example. Maybe if they are sick, they also like to dress warmer. Yeah? And whether it rains outside and whether you're sick, that should be independent of one another. But both might be correlated with the probability of people wearing something warm outside. And so the dependency is generated by some causal structure, and only because two variables, now let me say it the other way around. If two variables are dependent, then that is, of course, symmetric. But if three variables have a certain dependency structure, that doesn't mean that they all of them need to be dependent with one another. Sorry, do you see that screen here? Looks normal?
Yeah, we do. I'll just focus it so that, yeah.
Yeah, say this is your dependency structure. X1 causes X2 and X3 causes X2. Yeah, then if you look at the dependencies, then X1 and X2 will be dependent, and X3 and X2 will be dependent, but X1 and X3 will be independent because there's no causal link from X1 to X3. And I hope that answers your question.
Yes, if there's anything more, just please ask to clarify. So there are some others which have not been particularly voted, so we just go in any order. So
can I take the one by Zhenglin Li, because that's something that I need skipped in the talk?
Yes, sure, please.
Yeah, and I thought about whether I should put it in or not. So the question is, given a specific system, does only one min MCM exist? And the answer is it depends. There are two different notions of min MCM. There is latent minimality and edge minimality, and we explain that in detail in our paper. And for some systems, edge minimality, so the model with a minimum number of edges, and latent minimality, the model with a minimum number of latents, are the same, but they don't need to be. So unfortunately, the response is it's complicated.
Yes. Which one would you like to go for next? Because they're all equally, there's only one person answering. So.
Okay, so I see how are we to calculate the value of each various neuron? I have to say I don't understand the question, so maybe you can explain that in more detail, then I would be happy to answer that. And then there's Daniela. Hi, Daniela. Nice to see you here. So Daniela is asking, does this framework account for higher order interactions? For instance, two variables being together a cause for the behavior of a target variable with an influence that is different from the sum of the individual influences. Yes, it does, because structural equation models it can be of arbitrary form. And if you would have a linear structural equation model, then you would just have the sum of the influences. But if you have non-linear functions in your structural equation model, then of course you can have such interactions. And in our min-MCM approach, the way that we estimate these dependency matrices, that can be with linear methods like correlation, or it can also be with non-linear methods like distance correlation or Hilbert-Schmidt independence criterion. So all of this is also applicable to higher order interactions.
Great. And there is a slightly, I don't know about quantum consciousness.
Okay, let me read this one. So this one was like quantum consciousness or discrete attention modeling at the causal level, which may be unconscious but emerges at a higher level of attention as probabilities bundled together and reach a neuronal threshold. Oh, sorry, I have no idea. Yeah.
Yeah. Well,
it sounds fascinating to think about these things, but I do not have any good answer for this question at this point.
Yeah, I guess that's probably the most that can be often said about these very higher level questions. Okay, so we are done with that. Maybe I could also ask you something, which is you mentioned the tau and omega transformations to go from one level to another.
Yes.
And I was just wondering if these are these somehow related, or do you really require these two? Because one is for transforming the causal graphs and one is to transform the do calculus. So I don't know if they should be related or they should be not.
Yeah, it's pretty tricky. And to be honest, we're currently still working that out ourselves. So you can come up with examples where you have a causally consistent mapping for a given tau if you only consider a subset of the potential possible interventions. But if you consider all interventions, then it's not consistent anymore. And I would say if these tau, this tau transformation is in a sense the true causal relation in the model, then I think the tau and the omega are probably the same. But if you want to abstract it, then I don't think they are. But as I said, I think it's a very tricky question, and we're still grappling with that right now as well.
Great. And maybe I can just go ahead with one more if we have a little bit more time, I guess. Yes, we do. And in the meanwhile, people feel free to ask if you have anything more. So also wanted to ask you about dynamical models. How would those fit in?
Yeah.
Yeah.
Yeah, thanks for that question. That's one of the big criticisms of these structured equation models. But how do you model dynamical systems with that? And in principle, I think it is possible because you could model, let me go back to this Xono page. Let's say you have a dynamical system, you could model your variables at different time points. And then every time point would be a new variable of its own. And then you do get some directed acyclic graph from that. So in principle, you can apply this framework to dynamic systems, but you blow up the number of variables, making inference very hard and maybe even impossible. And there are some people who are working on extending these structured equation models and causal inference to dynamical systems. Joris Moy in Amsterdam, for instance. And it would be very exciting to think about whether you can also find consistent transformations between SEM representations of dynamical systems. But I have to say that is nothing that we have thought about so far.
I see. So effectively, as I see it, it's just essentially increasing the number of variables, just that you unroll time in some sense.
Yes, exactly. Yeah. And of course, that can blow up really, really fast.
Yes. Great. So there are no other questions. And so we thank Moritz again. This was a fascinating talk. And it's also, please show your appreciation on the chat box. We cannot, of course, invite you all. And it will be available on YouTube for further viewing. So, again, thanks, Moritz, and great to have you. And
thank you very much, Aditya, and thank you all for attending and asking questions.
Great. Okay, goodbye, and see you at the next talk. Yes.
Thank you. Bye-bye.